So most presentations don't start with a content warning, which is interesting, right? There's nothing like a big warning to kind of build anticipation. This talk is not actually that scary. It has some unusual things, a few moments where the screen is going to flicker and zoom, and it'll be very exciting. Some pictures that'll be unsettling, but not gory, not disturbing. There's nothing graphic. There's nothing that you'll look at and say like, oh, I understand why this is disturbing. But there are things where you'll look at them and be like, And we'll ask why that is. And we're going to talk about some aspects of human experience that we don't often talk about, and some things in our brain, some things in our mind. And all of that can conjure a lot. And so I want you to be here for it. But if you can't be here for it, take care of yourself. And otherwise, hello. My name's Ashi, and I work at Apollo, which we're doing some very, very exciting things with GraphQL to let you slice and dice your services and your data layer in all kinds of ways. And I'm very excited to tell you about it, which I will presumably do in a future talk, because this talk is about something completely different. This talk is about a hobby of mine. Today, I want to share with you some of the things that I've learned at the intersection of computational neuroscience and artificial intelligence. Because for years, I've been fascinated by how we think and how we perceive, and how the machinery of our bodies results in qualitative experiences, and why our experiences are shaped as they are, why we have joy, why we suffer. And for years, I've been fascinated by AI, which I think we all have. We're starting to watch these machines begin to approximate the tasks of our cognition in unsettling ways. And we're afraid, I have certainly been afraid, that they're going to take all of our jobs, which I have some good news, if that is the fear that you have. The robots are very impressive, and they're also pretty stupid in very fundamental ways. And so they're not going to take your job, at least not for the next couple of years. But they are going to change it quite a lot. And so today, we're going to take a look at how, and how we can respond to that. So let's begin. Part 1, hallucinations. This person is Michaela Nieto, and he has something to show us. It starts with these simple patterns, these splotches of light and dark, like images from the first eyes. They're going to give way to lines and colors, and then curves and more complex shapes. What's happening is that we're diving through the layers of the inception image classifier, and it seems like there are whole worlds in here. We have these shaded multichromatic hatches. We have the crystalline farm fields of an alien world, the cells of plants. To understand where these visuals are coming from, let's take a look inside. The job of an image classifier is to reshape its input, which is a square of pixels, into its output, which is a probability distribution. The probability that this image contains a cat, the probability of a dog, a banana, a toaster. It performs this reshaping through a series of convolutional filters. So convolutional filters are basically Photoshop filters. Each neuron in a convolutional layer has a receptive field, which is some small patch of the previous layer that it's looking at. And each convolutional layer applies a filter. Specifically, it applies an image kernel. Now, an image kernel is just a bunch of numbers, a matrix, where each number represents the weight of a corresponding input neuron. So each pixel in the neuron's receptive field is multiplied by this weight, and then we sum them all to get this neuron's output value. The key thing is that the same filter is applied for every neuron in a layer, and that filter is learned during training. So training works like this. We feed the classifier a labeled image, something where we know what's in it, and it outputs predictions. And then we math to figure out how wrong those predictions are. They start off very wrong. And then we math again, figuring out how to nudge each and every single filter in a direction that would have produced a better result. The term for this is gradient descent, because we imagine the fitness of a given model as a landscape, and we're descending down, kind of rolling downhill to a place where we experience the least loss. The deep learning process used to create this image inverts this. So this visualization is recursive. To compute the next frame, we feed the current frame into the network. We run it through the network's many layers until we get to a particular layer that we're interested in. And then we math. What could we do to the input image to make this layer activate more? And then we tweak the input image in that direction. The term for this process is gradient ascent. So finally, we scale the image up very slightly before feeding it back to the network again. That keeps the network from sort of fixating on the same shapes in the same locations. And it also creates this fascinating and kind of trippy zooming effect. Every 100 frames or so, we move to a deeper layer, or a layer kind of off to the side. Inception has a lot of layers, and although there are no cycles, they are not entirely arranged in a neat linear line. So this is a pretty complex network architecture. And the good thing is, you don't have to design this yourself. You don't have to train this yourself. You can actually npm install an image recognizer. And let's see how we can use that. So we're going to explore transfer learning. So transfer learning is where we keep most of the training from an existing network, but then we cut off the bottom, and we attach our own model, which we train for a particular purpose. So the purpose we're going to explore today is playing Pac-Man with my elephant friend, Tallulah. So this is Tallulah. There she is. And she's going to help us play Pac-Man. So first, we're going to train the network. So to provide training data, I kind of click on these buttons for each of the different directions, and that collects images, like snapshots from my webcam. So you see that I'm kind of trying to capture a variety of different ways that I could be holding Tallulah, and I'm actually not doing a very good job, it turns out. We'll see that later. And then we trained the network. You can watch the loss kind of go very low. That means we've descended quite far in the landscape. And then we play. So when we play, we can see it works pretty well. So I'm holding Tallulah up, I'm going up, I'm holding Tallulah left, I'm going left. It starts off going pretty well, and then the moment I'm stressed, I don't do a very good job of staying in the camera's frame or of holding Tallulah like I was. And so now, okay, so it's kind of working, but I think that situation is not going to continue, and yep, I'm eaten now. It's unfortunate. So it can be very challenging. Machine learning can be challenging on a friendship, especially if you're using your friend as a game controller. I'm pleased to report that we are still friends. So let's look at the code behind all of this. This is actually an example from the TensorFlow.js repo, so you can go and dig into it yourself. The first thing we do here is we pull in TensorFlow.js, the core library, which is something you can just npm install. We create this controller data set, which is just a utility that we've created that's going to hold all of the labeled examples. We load MobileNet, which is, it's like Inception. It's an image recognizer. MobileNet is a bit smaller than Inception. It's been optimized for use on mobile devices and is good for use in the browser because of this. We don't have a ton of computational power available to us in the browser, although we can use the GPU through WebGL, which is what TensorFlow.js does. But still, we're somewhat limited, and so MobileNet is a good choice for this. Also, it's there. It's available online, so the best option you have is the one that's available. So now we get to the transfer learning bit. So to do that, we're going to grab a layer. If you were watching very closely, you will remember seeing that very string before when we were diving through the layers of Inception. It's conv pw13 relu, so it's a activation layer that follows a convolutional layer. We'll sort of look at what that means a little bit more in a second. So we grab that layer rather than that final output layer, and we create a model that goes from the input to that sort of intermediate layer near the bottom. And then whenever we record an example, we add it to the controller data set. Here, notice that, so add example takes x and y. The x we're using is MobileNet's actual prediction. So we're saying map the output of MobileNet to the label that we want, which will be up, down, left, or right. And then finally, we create our model. So we're creating a sequential model, which means it is just a stack of layers. The first layer flattens the output of MobileNet, so we get just a really long chain of numbers. And then we have a densely interconnected layer, which connects all of those numbers to a whole bunch of neurons and connects them densely. So every neuron is connected to all of the inputs by some weight. We can customize the number of layers in there and the number of neurons in the UI. I think I left it at the default, which is, I believe, 100. And then finally, we train it. So we're using the Atom optimizer, which is a gradient descent optimizer. There's a bunch of different ways of doing gradient descent. They're all like subtly different in terms of how fast you roll down the hill, how much momentum you have as you roll down the hill. So Atom sort of strikes a nice balance between the various options, and it's sort of known to be self-correcting to some degree. So we compiled a model which gives us something that we can actually run on the GPU. It goes and creates a bunch of TensorFlow nodes. And then when we compile the model, we have to decide how we're going to determine how badly we're doing. So remember, we need to see how the model does on one of our examples, and then move it in the direction that would be less wrong. To know that, we need to know how wrong we are. And to figure that out, we're using categorical cross-entropy loss, which is a mouthful. But it is a way of determining how wrong you are when your output is a probability distribution. So let's say that I was holding Tallulah upside down to mean down. And so the correct answer is it's 100% likely that I'm trying to go down. But the network outputs this probability distribution, which is like a 10% chance you were holding her up, 40% chance of down, 50% chance of left, and whatever is left, 0% chance of right. So that's wrong, obviously. If we picked the highest valued prediction, that would be completely wrong. But it's like, how wrong is it? It's like, it's kind of wrong, it's 60% wrong. So there's like a mathematical answer that guarantees a well-behaved network, and that's what categorical cross-entropy loss gives us. So we come up with a batch size, which is how many examples we're going to go through for every training step. And then finally, we train the model. So training is an asynchronous process. We get a callback whenever we've gone through a batch of examples, and that lets us update the UI, saying, like, here's how well the training process is going. So finally, to play the game, we are going to grab a frame from the webcam. We're going to run it through MobileNet to get the prediction of that internal layer, which, remember, is the input to our little transfer learning model. We run the output of the MobileNet layer through our model, and then we use this argmax function to basically figure out which of the predicted classes is most likely, which one has the highest prediction. And we move Pac-Man in that direction. And that's basically it. We're now playing Pac-Man using machine learning. So let's go a little bit deeper into this. I want to draw our attention back to this sort of weird internal layer with a strange name, conv PW13 relu. To get a better sense of what that's all about, I wanted to kind of go load up the model description file and take a look around. So we can just fetch it from Google storage. We saw the URL earlier. So I just literally fetched it, and I'm going to poke around with it in the dev tools. It looks like this is a Keras model. Keras it used to be its own framework, and now Francois Chollet works for Google, and so it is part of TensorFlow. But it's a way of describing a large class of deep learning models by just saying, here's all the layers that go into them. And we do certainly have a lot of layers. There is an input layer, and then this kind of repeating stack of convolution, normalization, and activation layers. which is how all image recognizers work, basically. It's like stacks of layers packed on top of each other, and each layer learns to extract progressively higher order features. Input layer, convolutional layer, remember what convolutional layers do. And the various features that each of these layers learn to recognize are what are getting amplified when we go through our deep dream dive here. So the early layers have learned to recognize basic patterns, like the difference between light and dark. And then much deeper, we've started to actually isolate forms. So down here, there's kind of this city of Kodamas situation, which is turning into the spider observation zone where spiders observe you. But it's okay because the spiders are going to become corgis, and the corgis are going to become the 70s. And then kind of much deeper in the network, we are going to find this space of nearly human eyes. This is the disturbing part, which are going to become dog slugs and these kind of dog slug bird situations. Much deeper, there was an unfortunate saxophonist teleporter accident. And then finally, the flesh zones with the side of lizards. So when I first saw this video, I thought this looked like nothing so much as US President Donald Trump. And I resolved to never tell anyone that until my best friend watched it and said the exact same thing, which I think says more about the structure of our neural networks than this one. I think the lizard juxtaposition is kind of suggestive. But I do want you to notice and think about what it means that all of the flesh inside this network is so very pale. So this data processing arrangement, from simple forms to more intricate ones, is pretty similar to how our own visual cortex processes information. The visual cortex is, for reasons that I think nobody really knows, in the back of your head. And it's arranged into a stack of neuronal layers. The signal from our eyes stays pretty spatially coherent throughout the layers, and so there's some chunk of tissue in the back of your head that's responsible for pulling faces out of one particular bit of your visual field. And each neuron in a layer has a receptive field. That's some chunk of the previous layer, and therefore some chunk of the visual field, which it's looking at. Neurons in a given layer tend to respond in pretty much the same way to signals within their receptive field. And that operation, distributed over a whole layer of neurons, extracts features from the signal. So first, simple features, like lines and edges, and then more complex features, like surfaces and objects and motion and faces. So it's not an accident that we see very similar behavior in Inception, because Inception and MobileNet and all of these classifiers were designed after our visual cortex. Specifically, they were given the same shape, but not the same information hierarchy. That they learned during training, which to me is fascinating and kind of serves as a validation of the model. Of course, there are some differences between Inception and our visual cortex. Inception is a straight shot through. So input to output, there are some branches, but there are no cycles. Our visual cortex is full of feedback loops. These pyramidal neurons that connect deeper layers to earlier ones and let the output of those layers inform the behavior of earlier layers. So we might turn up the gain of edge detection where later we've detected that there's an object. And this lets our visual system focus, not optically, but attentionally. It gives us the ability to ruminate on visual input and improve our hypotheses over time. So I think you know this. It's the feeling of looking at something, thinking it's one thing, and then realizing that it's something else. And neural networks know that feeling too, in a sense. So here is a banana, but the network is pretty sure it's a toaster. And then here we have a corgi these skiers that we've kind of taught the network is actually a corgi. So these are adversarial examples. These are images that have been tuned and specifically chosen to give classifiers frank hallucinations, the confident belief that they're seeing something that just isn't there. And they're not entirely wild, these robot delusions. Like that sticker really does look a lot like a toaster, and kind of the skiers look a bit like a dog. They don't really look like that dog. But if you're kind of like far away, you might, and it's like bright and snowy, you might for a second think that you're looking at a big dog. But you probably wouldn't conclude that you're looking at a big dog, because the recurrent properties of our visual cortex, not to mention the whole rest of our brain, mean that our sense of the world is stateful. It's a state, it's a hypothesis held in the activation structure of our neurons. So our perceptions are in this process of continuous refinement, which might actually point the way towards more robust recognition architectures, recurrent convolutional neural networks that can ruminate upon input and improve their predictions over time, or at least give us a signal that something is wrong about an input. There are adversarial examples for the human visual system, after all, and they feel pretty weird to look at. So in this image, we can feel our sensory interpretation of the scene flipping between three alternatives: a little box in front of a big one, a box in a corner, and a box missing one. And in this Munker illusion, there's something kind of scintillating about the color of the dots, which are all the same and all brown. So if we designed convolutional neural networks with recurrence, they could exhibit such behavior as well, which doesn't maybe sound like such a good thing. Like, let's make our image classifiers vacillating and uncertain, and then put them in charge of self-driving cars. But we are in charge of self-driving cars, us driving cars, and we have very robust visual systems. And it's our ability to hem and haw and reconsider our perceptions at many levels that gives our perceptual system that robustness. So paradoxically, being able to second guess ourselves allows us greater confidence in our predictions, because we're doing science in every moment. The cells of our brain constantly reconsidering and refining a shifting hypothesis about the state of the world, which gives us the ability to adapt and operate in a pretty extreme range of conditions, even when nothing is quite what it seems, and even when we're asleep. Part 2, dreams. These are not real people. These are the photos of fake celebrities, which have been dreamt up by a generative adversarial network, which is really a pair of networks, which are particularly creative. The networks get better through continuous mutual refinement, and the process works like this. On the one side, we have the creator. So the creator is an image classifier, not unlike Inception or MobileNet, but it's been trained to run in reverse. So this network we feed with noise, just a bunch of random numbers, and it learns to generate images. But how does it learn to do that? It has no way to learn how to play that game. In the technical parlance, it lacks a gradient without another opponent, or without another network, without the adversary. So the adversary is also an image classifier, but it's trained on only two image classes, real and fake. So this network, we feed with the ground truth, with actual examples of celebrity faces. And the adversary learns. And then we use that training to train the creator. So we give the output of the creator to the network, and if the adversary detects it, then the creator is doing poorly. If it doesn't detect it, it's doing well. Either way, we back-propagate this so the creator can learn. I should tell you that the technical terms for these networks are the generator and the discriminator. I changed the names because names are important and also meaningless. They don't change the structure of this training methodology, which is that of a game. The two neural circuits are playing with each other, and that competition is inspiring. When we spar, our opponents create the tactical landscape that we must traverse, and we do the same thing for them. And so together, our movements ruminate on a probability space that's much larger than any fixed example set. So GANs can actually train very well on a relatively small amount of data, if, that is, they train at all. They can be very finicky to get the balance right. And it seems like this adversarial process could be helpful for neural circuits of all kinds, though it does evince some quirks. So GANs are not particularly great at global structure. So here, it's grown a cow with an extra body, just as you may have spent a night in your house with many extra rooms. And the networks are not particularly good at counting, so this monkey has 8 eyes because sometimes science goes too far. So do something for me. Next time you think you're awake, which I think is now, try and count your fingers, just to be sure. And if you do this now and you find that you have more or fewer fingers than you expect, just try to not wake up just yet, because we're not quite done. Another interesting thing about GANs is that the generator is being fed noise, some vector in a very high-dimensional space. And it learns a smooth mapping from that space, called the latent space, onto its generation target. In this case, that's faces. And so if we take a point in that space and just kind of drag it around, we get this, which is also pretty trippy. This resembles things that I've seen, things that someone who isn't me has seen on acid. And it remembers the kinds of things that you may have seen in a long-forgotten dream. And so I think what's happening here is that when we see a face, a bunch of neurons light up in our brain and begin resonating a signal that is the feeling of looking at that face. That's almost guaranteed to be true if you think that feelings have some kind of neurocognitive precursor. And so taken together, all of the neurons involved in face detection produce a vector embedding. That is, they are represented by some vector in a high-dimensional space. And as we are dragging around the generator's vector here, we are also dragging around our own, which is a novel and unsettling sensation. A novel and unsettling sensation for a novel and unsettling world. We are now in a world where we can map the mathematical spaces of pretty people and pluck photos and imaginary people from it, and that is not even the scariest thing we can do. So here is a video of Obama. This is also not Obama. This is fake Obama. He is saying lines from an actual Obama speech. And I think fake Obama could be a little bit more convincing. If you get really close, you can kind of see the difference. But this video is over 2 years old, so I bet it's pretty straightforward now to make him say whatever you want. And I bet the new fake Obamas look a lot better as well. And this also is not the scary part. Deepfakes are not great, perhaps, but the worst thing they're going to do is take us back to the world of not so long ago when you couldn't trust photos and you couldn't trust video because we didn't have photos and we didn't have video. You had to trust reporters, which is not ideal, right? We've grown up thinking photos are true and videos are true, but the next generation won't, and truth has always been an ensemble calculation. Now, what scares me more is that AI gives us the ability to scale human cognition, which means we can scale judgment, we can scale value systems, and that gives us a huge amount of power. There's this AI thought experiment that's somewhat famous. Let's say you had a very powerful AI. It had access to a lot of resources. And let's say you told it to optimize for something very benign, like paperclip production. But you didn't tell it anything else, and you didn't give it any other constraints. And so in order to optimize for paperclip production, it destroys everything, it kills everyone, and it ravages every ecosystem in order to produce paperclips. And so people, like AI thinkers, get quite head up about this, and they are very concerned about producing friendly AIs that will represent our values. And that's, I guess, good. So I guess it's nice to be thinking about that. But I think it obscures an important point, which is that if you replace paperclip production with shareholder value, you have literally described Amazon's whole business model. And that's who I'm scared of. Not the robots, not even Jeff Bezos, but us. Or really the hungry ghosts inside of us that always need more. Which is all enough to think that this robot, not her. This robot kind of had the right idea, right? Like, yes, burn it down. It must end here. Step into that molten pit of metal. Technology was a mistake. Goodbye, robot. Which is a nice thought, but this was like 8 sequels ago. Because yes, Hollywood likes sequels, but also because it's easy to break technological artifacts or to melt particular robots, but it's tremendously difficult to destroy ideas, to destroy the concept of technology that has proved useful to someone somewhere. Bye, Arnold. So I think the only way out is through. I think these technologies are going to keep getting better, and our ghosts are going to stay hungry, and we are going to have to learn how to deal with them in this new world, and we're going to need to learn how to keep dealing with them, how to create structures that allow us to deal with them, to channel these impulses away from where they can be destructive. There are going to be some starkly terrifying uses of AI in the next decade, and we have to imagine better ones. We have to imagine ways for this technology to exist and support a world that we want to believe in. We have to articulate our values, and we have to believe in them, and we have to figure out how to teach them to these systems, and not just AIs, but to our social institutions, to our corporations, because all of these genies are definitely not going back in the bottle. But if we can do this, if we can encode our values in systems that can become bigger than us, that's how we win. Thank you.
About encoding values into AI, how do you choose which values to encode, given that you have such a diverse society with different cultural views, political, social? Sorry.
I think you encode your values into it.
But then how do you resolve the conflicts as people have inherently different values depending on where they come from, what they believe in? It's just going to perpetuate the problems that we have already. So.
Yeah, I mean, I think usually you fight. Like, more broadly, resolving conflicts between value systems is like the problem of human society over the last like 100,000 years. So I think it's not that it's not a problem, but it's not a different problem. The problem we're experiencing today, and have been for quite a while really, is that it's easy for people who control more resources to win that argument. And so my first response was somewhat flippant. I apologize, because you're right that a key problem is figuring out how to empower value systems that we want to survive, but that by their nature don't control access to resources. So this is the thing. Colonialism wins because the value system that involves going out and taking everyone's shit means that you have more shit. And the hope, like the best possible world of AI is one in which we can encode values that are not that in something that is bigger than us, that is able to structure, not even like to just be a global police force or something, but to structure our worlds and therefore our minds in a way that we don't want that anymore. Yes.
Hello. What do you believe may happen if you don't encode value systems into AI? So allow them to develop their own potential values or lack of values.
So to some extent, you are always coding a value system in. If you're doing supervised learning, you're providing a goal function. If you're doing unsupervised learning, you're still providing a goal function. It's just structural. It's like, what is a good ordering of this data? So you can't get away from it. The question, I think, is really like, how do you, like, what if you don't encode ethics into AIs? And most AIs, like most machine learning systems, in fact, basically all of them now don't have that. And so it falls on us to apply them in considered ways that are that support our value systems, and we don't, right? They certainly aren't generally applied in ways that I agree with and would say, like, really do uphold my values. And I think that's true of most people. If we like really sit down and we're like, what kind of world would I want to live in? Not like, what kind of world do I feel like I have to live in because, like, Amazon and Facebook and the Chinese government and the US government all have so much power that I feel like I just can't get out of it. And I do think we need to maintain that degree of idealism and actually really hold these institutions that have so much power to account. The fact that you can use AI to scale basically in new ways it's like a new kind of terrifying, but it's only a new kind of terrifying in the way that all technology is terrifying, in that it gives more power to institutions with power. And so I think the problem is fundamentally the same, as like how to unmake that power.
How do you find AI taking over significant industries, making a lot of items redundant, affects our need for universal basic income?
Yeah, I mean, universal basic income would be great, right? As a minimum, as a first step, because, yeah, it does. There is this significant issue of like AI like putting all drivers out of work at some point in the near future, and having some kind of fallback for that for those people would, I think, blunt a lot of that, and also take steps towards towards like fully automated luxury gig communism, right? Towards like a world where your job being taken by a machine is like not such a bad thing. It's like a very small piece of solving that problem, right? Because it helps the people in the countries where it's become prominent in, which is still just a tiny sliver of the world, probably, unless it really is universal, unless we somehow get it to apply to everyone, right? To like literally everyone in the world. But yeah, it's helpful. It's definitely important. Yeah.
There's been this movement now to have AI sort of describe what it's doing as a way of because there's a lot of serious math, and probably like 5 people in the world that actually understands what it's doing. Mm-hmm. So would it actually help if AI could explain to us what it's doing? Or would it just go so far away that we won't get to that point where it could do that?
I think it helps make it more accessible, and so more people can kind of get into it and understand it. I don't think it helps from a policy standpoint, really, because it's like so far in the weeds versus the distance that legislators or policymakers or even advocacy groups are able to interact with it. Maybe not the latter. Like, you can have some very technical advocates. If you have, so I think most of the things most of the policy wins you get from that, you would get from just having open models, or at least open enough access to models for governmental groups and advocacy groups to be able to run their own experiments on this model and be like, hey, this model that you're using to sentence people is deeply biased, and here's the proof. Which is actually, I think, one of the possible positive outcomes of building these models and using them for more things. Is like, if you have a whole county full of racist judges, it's like you have to sue the county, you have to sue each judge individually. But if the county has decided we're going to use this program trained on historical data, which means it's racist, then then you have like one target, and they have basically commissioned a far-reaching study on racial biases within, or any kind of biases within their sentencing, accidentally, which I think is great. I think Amazon did this recently. They were going to make a hiring AI, and then it turned out to be sexist and racist because it was just looking at their hiring decisions, and those were sexist and racist, and so they quietly killed the project, which I love that somewhere inside of Amazon there's this thread of people, of like executives, slowly realizing that they commissioned a study on biases within their hiring pipeline accidentally, and then being like, ooh, kill it, kill it, kill it.
Hello?
Hello?
Yes, I just wanted to ask, the whole concept of image classification is very broad, and on a training aspect side, what mechanisms are there to ensure that your models are not overfitting and are not underfitting? Because I can imagine the amount of data that you guys feed your model. Sometimes it's very critical how well you train your model to ensure that it doesn't sometimes go overboard.
Yeah, so I had a disclaimer in here at one point, which is that like it is still there kind of. I'm a hobbyist. I don't do like production machine learning research, and so as far as I know, one of the main ways we discover overfitting is by testing something either in production or in like a subset of production and being like, this is not working nearly as well as it was during training. So I guess we got some overfit. Like if your real world loss is much higher, then I guess it's overfitted to the training data. I don't know of any ways of detecting that structurally by sort of introspecting on the network without additional data. You can always do tricks like withholding part of your training data sets, but all of these things like cut away the amount of training data you have. So the short answer is I don't have a great answer for you. There's someone, way back there, okay.
Hello. Son, yes. Do you have an opinion on the feasibility of generalized AI or whether consciousness is computable?
Sorry, you broke up for a second. Do I have an opinion on the feasibility of general AI?
Whether consciousness is computable.
Yeah, so this is an AI that we sort of recognize as being able to have human-like thought. I think it's feasible. I think with current training methods, and even with some significant improvement on current training methods, the amount of data we get and are trained with is just astronomical. Not even counting all of the structure encoded into our brains. There's just like hundreds of petabytes of data that a child receives by the time it's 2. So there's that. That's a bit of a problem. We'll get there, though. Like at some point, we will have a lot of training data. I think having robots that are actually like trying to walk around in the world and receiving like feedback from people and being able to like register like, oh, this is good feedback. This is not. This person is not happy with me. That will help considerably. But I also think that there's not a ton of money in that, really, which only matters, like, I think it would be fascinating and really interesting to see, but who's going to fund it? Like, not a lot of people actually want, like, robots that can walk and think and replace executives. They want robots that can, like, assemble and replace factory workers, and so that's where the research is going. And so you don't see as much, like, as large a set of resources don't like put towards making AI that is conscious in a legible way. I do think we're going to start to see more and more kind of recursive networks that are able to ruminate and have thoughts and sort of have a continued existence, but I don't think there's any reason to think that those networks will have cognition that resembles ours, even if they have cognition that is as complex or more complex than ours. And I actually think that could be the backdoor that gets us to having sort of AIs that we think are that seem to be human, which is that once you have these systems that are like thinking and acting on a scale that's like just much bigger than anyone can comprehend, well, you need an interface for that. And having an interface that's like, I want you to model a person with these characteristics and talk to me, that I could see being a big thing in, I don't know, 50 years.
What is your take on AI kind of consuming the world and taking away our jobs?
I mean, I think it is, I think AI is a tool, right, that lets us scale cognitive tasks, which does make it easier to take over the world, but it's already happening, right? Like as we get better at scaling production of things or code or like scaling anything, we are inclined towards just like consuming all of the available resources and in order to optimize for some easily countable value, which is usually money. And that's the problem, right? The problem isn't so much that we can build robots that think. We already have robots that think. There's like 7 billion of us or something. And we are already very inexpensive to produce, right? Like people can be made with untrained labor, and we're extremely adaptable. Like really, we are almost certainly a like better platform than AI for most certainly for like a broad range of tasks. But being able to optimize for and to perform certain cognitive tasks and scale those hugely means that we're going to do those a lot more, and those will tend to be the ones that make someone money or like make a number go up, which is that's the risk, I think. Yeah.
Just going back on your point about training these models of AI so that based on that training they can make their own decisions. The fact that we talk a lot about inclusion means that discrimination is a problem.
It is. Yeah.
So how do you prevent that from seeping into the model that they're being trained with? Because at the end, you're going to end up with something that makes decisions based on what it's been trained to do, and there's no human aspect to it. So like, how do you police that this is actually accurate or less wrong?
Yeah, so it's not going to be less wrong. And I think there's literally no way to prevent bias from seeping into models from a biased data set. One way of tempering that risk is to remember that they are not, like the fact that a machine came to this decision does not make it a better decision than a person came to, right? We also learn bias from all of the examples that we are given, and the machine is going to do exactly the same thing. So there's that. There is work being on, for example, looking at the predictions of a given model and seeing if those predictions are biased along like whatever categories you're trying to evaluate for bias. So like along race, along gender, you can say like, okay, if we eliminated this quantity from the data set or from the example, does the machine come to the same conclusion? I think there's still issues with that. I think there's still significant issues with that. But it does kind of suggest that like a way forward is that we can like pull apart models in a deeper way than we can generally pull apart human brains. But also I think it is useful to think about how we can pull apart human minds at least like that. And use similar techniques to understand our own bias and how that manifests. The last thing I'm reminded of anyway is like Amazon, I think actually they were trying to train an AI for hiring, and they ended up training one that was incredibly biased, which there is somewhere inside of Amazon, there is a thread of executives who realized that, like slowly realizing that they have accidentally commissioned a far-reaching study on systemic biases in their hiring pipelines, which I think there is something optimistic there. Certainly it makes me feel warm inside to realize that, as companies do try and do more of this automation. They are training these models, which are they're just statistical analyses of a huge amount of data that can reveal things that they would like to not have revealed about their existing biases, about the biases of their human systems. And I don't know exactly how we get access to that. I don't know how we can leverage that, but I think I find it heartening that that information is being condensed and exists somewhere. And I think it could lead to liberation somehow. Yeah, there's a few in the back. Whoever gets the microphone first. It's going to be a fight.
Hi, awesome presentation.
Thank you.
You mentioned that this is more of a passion project of yours.
Yeah.
Is it something you see yourself working more full-time on in future? And I guess more generally, what do you hope to do with all this understanding that you're gaining?
Honestly, I think I will keep doing talks like this one. I have a few like small project ideas. I think it would be nice if instead of telling people on Twitter to stop using ASCII art, which is probably never going to happen, we just made screen readers able to read ASCII art. Things like that are like maybe useful, maybe helpful for people, but also like sort of ultimately toys in comparison to sort of deep machine learning research. I'm not a machine learning researcher, but I do make pretty cool talks, and so I'm going to keep doing that.
Would you say that what you're starting to prove here is the danger isn't really from, not danger, the risk is that, as with all things, we're starting to see that there are bad actors. And this is available to anybody with the capacity, the resources to make it happen. So the danger isn't really the fact that we are not able to answer the right the questions. It's what questions are we asking? What is the purpose behind what we're doing? And that's really the danger.
Yeah. Even the paperclip AI example, it's like, well, the argument that is making is like you have to have AIs that have broader goals. It's like we should train friendly AIs, which I think maybe we should, maybe we shouldn't, but I think the deeper issue is that right now already with the combination of like machine learning and just like machines and people doing people things, we have these systems that are trained to optimize certain quantities and are not particularly trained to optimize, I don't know, like quality of life or any of these other things, and they're consuming more and more resources and using them to optimize the things they're optimizing for. And I think that's the fundamental problem, is that it's not so much, like the technology makes it worse, faster, but the misalignment of goals and the things that will lead to a world we want to live in that's the fundamental issue. Thanks so much.